let's talk about conservation of momentum. So if something is conserved, it just means it's same before an action and after. Okay, so we talked a lot about conservation of energy in Physics 20, and now we're going to talk a lot about conservation of momentum in Physics 30. So and that's just saying that the total momentum of a system remains constant as long as no external forces act. So when we're talking about momentum conservation, then we're talking about not necessarily isolated systems, but definitely closed systems. If we look at a closed system, then we will always have a conservation of momentum, meaning momentum before should equal to the momentum after collision or just some sort of action, okay? And so we take all our momentums at one point and sum them of however many objects we have in the system, and then the momentum afterwards and sum those, and it should be equal, of course. So that's what the sigma means. Remember, if you just forgot from Physics 20, this of course means sigma, which means to sum, or the sum of, or the summation. So basically the sum of all the momentums P at one point is equal to the sum of all the momentums P prime at one other point. So a great example of this is rocket propulsion. This is the basic principle on which we launch rockets on. So basically, if a rocket is at rest, its momentum is zero. How do we propel it forward? Well, we expel gases backwards, which then propels the rocket forward, because if the momentum, mass times velocity, before is zero, afterwards should still be zero, that doesn't mean that there's nothing moving afterwards. It just means that the momentum of the gases being expelled downwards should be equal and opposite to the momentum of the rocket upwards. So as it dispels gases, it loses its mass, which then changes its velocity, making it go upwards. And so then its net momentum afterwards is still zero, because of course momentum is a vector and we care about direction. So that just means the momentum downwards is numerically the same as the momentum upwards. Okay? And so that's conservation of momentum. So again, we're just looking at something. If we have a collision, or if we have an explosion, or we have something like that, the momentum before should be the same as the momentum afterwards. And that's, of course, in a closed system, not in an open system, because, of course, this is only when no external forces are acting. So with the rocket, the only forces acting are the ones within the rocket. So today we're just going to look at one-dimensional conservation of energy. So if there's just something happening horizontally or vertically or something like that, we're not going to look at 2 dimensions yet. That's in the next lesson, where things do get a little bit more complicated, because of course momentum is a vector. So if we're in 2 dimensions, then we need to break it down into our 2 dimensions. So let's just start with one-dimensional conservation. Make sure you understand that before going on to 2 dimensions. And so here we don't have to worry about x and y directions. We just say the momentum before is equal to the momentum afterwards. And so, of course, you basically have the sum of all the momentums of the objects in the system. Okay, so there could be object 1 and object 2, and so you take their momentums beforehand, sum them, and then, of course, the object 1 and 2, afterwards, you take their momentums and sum them as well, and those should be equal and opposite. So a great example of this is 2 billiard balls running into each other and bouncing off and going in the opposite directions. So again, we would have to have the mass and speed of one of them and the mass and speed of the other one. And of course, direction does matter in that case. So we know that they're going to opposite directions, are going to opposite directions afterwards as well. And so that will also play into it. Okay? So that is conservation of momentum, just looking at if no external forces are acting, the only forces are the ones within the system, then we have a conservation of momentum before and after. Okay, and so then we can use the sum of our momentums before equaling the sum of our momentums afterwards to usually find the speed of something after a certain collision or something like that. So for example, Say we have a child on a boat and he throws a 5.40 kilogram package out horizontally with a speed of 10 meters per second. Calculate the velocity of the boat immediately after, assuming it was initially at rest, meaning its initial momentum was 0, so its final momentum should also be 0. That doesn't mean that things aren't moving, just means they're moving at opposite directions with the same momentum, because then they will sum to 0. Mass of the child is 26 kilograms and the boat is 55 kilograms. So we know that there is still going to be a change of momentum here because the child's throwing the package. So they're not only is the boat losing weight, but there's also then a new velocity going forward. So therefore the boat must go back, of course. And this is a great example because then there's no friction acting on the boat, or we'll assume very little, much less than if I were to just sit in a chair and throw something. I might not move back, but that's of course because of the external force of friction. Okay, so before, it's always helpful to draw a diagram, of course. So before we have our lovely little boat, right? And here's our kid who's gonna try to throw this package off of here. Okay, so we have no speed of the boat, right? The speed of the boat and the child is 0, so I'll call that VB. The speed of the package is 0. Okay, and then afterwards, the boat has lost some of this mass because the kid has then thrown the package off there. So there's the kid, and here's the package. It's over here on its way doing that. So there we go. The velocity of the package there is 10 meters per second. And we're trying to look for the velocity of the boat and the kid. We're trying to figure out what they are. So I'm going to put little ticks here to say that that's afterwards. And that's usually the convention we use in momentum to describe before and after. Okay, of course, I also need a positive direction and negative direction, so we will do that. But when I'm looking at my conservation of momentum, so again, I have all the sum of momentums before is equal to the sum of momentums afterwards. Again, I put that little tick there to say that that's afterwards. That I'm looking at, well, it's all one system before, but still, we're still looking at two different things. So I'll have momentum, mass of the boat times the velocity of the boat before, plus mass of the package times the velocity of the package before, which are, of course, both 0. Is equal to the mass of the boat times the speed of the boat afterwards, plus mass of the package times the speed of the package afterwards. Okay, and again, I put those little ticks there to say, well, that's going to be afterwards. So these guys are both 0 beforehand because we're assuming they're at rest initially. Okay, and then one other thing I need to do is I need to define a positive direction. Obviously, here we don't really have positives or negatives, but based on my diagram, I'm going to go ahead and say to the right is positive, so the direction the package is going in is positive. So we should just get a negative answer for the speed of the boat. Okay, so we have the mass of the boat and the kid. We have the mass of the package and the speed of the package. So I should be able to just rearrange this for the velocity of the boat and the child, right? I would subtract the momentum of the package afterwards from both sides, and then divide by the mass of the boat and kid, okay? And that's really all that we have to do. So this is how conservation of momentum can really help us out, because again, we know momentum before equaling momentum afterwards. We know momentum is mv, and so we just take a look at that, and we can then usually rearrange and solve for different velocities at different points. Okay, let's plug in our numbers. So remember to add the mass of the boat and the child together. And when we do that, we get negative 0 point. How many significant digits do we need? Well, we got 3 there, 3 there, 3 there. So it looks like we should probably have 3. And that is 0.667 meters per second. Again, my negative there is telling me direction, so I don't actually need to put a direction on there. However, if you did not make this guy positive here, you still would have gotten a negative, but you didn't define a positive direction. So there, you should probably put backwards or something like that, indicating direction. So if you are not using signage and you are not defining a positive direction, even if you get a negative, you still need to qualify that. So in some way, shape, or form, you need to qualify direction and what that means. So here we have a halfback on an apparent breakaway for a touchdown. Is tackled from behind. I know football. Yeah, doesn't that make me sound like I actually know what's going on in football? That's what it's designed to do. If the halfback has a mass of 95 kilograms, moving at 4.1 meters per second, when he was tackled by an 85 kilogram cornerback, running at 5.5 meters per second in the same direction. So that's pretty important because, again, if we want to look at conservation of momentum, well, it's defined by direction. So these guys actually overwhelmingly have a lot of momentum in the exact same direction. Then we want to know what's their mutual speed immediately after the touchdown saving tackle. So first we have the two things separate with their separate momentums, and then afterwards their momentums, of course, are combined because we have the combined unit of those two together, of course, because one guy's holding on to the other while he tackles him. Okay? So again, it's always nice to draw a diagram. I at least find it helpful. Always do kind of a before and afters type thing. Of course, sometimes we don't want to draw people, so do the physics mainstay of just drawing boxes, because, I mean, why not? Okay, so the mass of the cornerback is, what was it? So that's the cornerback. So he's 85 kilograms, and he's going at a speed of 5.5 meters per second. And then we have the halfback. And the mass of the halfback guy is 95 kilograms, and his speed is 4.1 meters per second. Great. And then afterwards, what does it look like? Well, afterwards they're going down together. So right here, they're, I'm assuming they're going that direction. It doesn't actually give us a direction, but we know they're overwhelmingly in the same direction, so we shouldn't even have any negatives here. Okay, and so afterwards, they're basically going to be together here, right? So then we have our cornerback and our halfback together going towards the ground. And so then we have a combined mass. I'm going to call that MCH because it's the cornerback and the halfback together. And so we get 95 and 85. So what's that combined mass? That should be 180 kilograms, right? And then their velocity together is, well, we don't know. Okay, so I'm going to call that CH because they're together afterwards. So when we do the sum of momentum beforehand and afterwards, it might look a little bit different this time, but that's fine. So I'm always going to preface conservation of momentum with this statement. I know it's gonna start to get a little bit repetitive to you. You're just going to start going, okay, why are we always doing this? But again, what you're doing with that simple statement is you're stating, this is a situation in which I have conservation of momentum. So it is really important when you're doing this kind of question, conservation of momentum question, to actually write that, because that's what you're communicating to the person reading your work, is saying, this is conservation of momentum. And that's kind of what we do in physics. We still try to communicate as efficiently as possible, which is why we don't write words down. But by writing these symbols, you're saying, okay, I know that this is a conservation of momentum question. Okay? So that means that their individual momentums before. So momentum of the cornerback, momentum of the halfback should equal their combined momentum afterwards, because they kind of become one unit. But there's still two parts, right? It's still a closed system. because there's still an exchange of energy, but there's no external forces. Okay? But they are combined afterwards, and so we still have our momentum before equaling our momentum afterwards, because these are the only two parts of this sort of unit or this thing. Okay, so I'm looking for the speed of the unit, the cornerback and the halfback together afterwards. I'm going to go to the next page just because I am running out of room. I'll write this all down again. May have written it in the wrong order, but hopefully you guys get this. So their combined velocity afterwards, well, really I'm just dividing both sides of their combined mass afterwards, but otherwise this is kind of saying the same. So this is a nice easy one to rearrange. And that's what I'm going to do. I'm just going to plug in the numbers now, and I should be able to get the velocity of their combined masses afterwards. And once you work all that out, afterwards we should have, I should be putting a little ticky guy on that to say that it's afterwards. After all that, we should get a final velocity of 4.8 meters per second. Okay, so we know the momentum changed because their combined mass changed. Well, it didn't change like in the whole system, but as soon as we change their individual masses to be a combined mass, we know the velocity has got to change as well. Okay, so there we go. Another way to use conservation of momentum, which is really very similar to what we have already been doing. Okay, let's do one more example. 15 kilogram bullet strikes and becomes embedded in a 1.10 kilogram block of wood placed on a horizontal surface just in front of the gun. If the coefficient of kinetic friction between the block and the surface, okay, so we have friction happening. So here's what's important is I know that once there's friction, that's an external force. So as soon as that happens, I cannot look at conservation of momentum anymore because that's an external force that wasn't present when the person first shot the bullet. Okay? So that's really, really important to note. So let's keep going though. So the block is on the surface. The block has and the surface have a coefficient of friction between them of 0.25. The impact drives the block a distance of 9.5 meters before it comes to rest. Why does it come to rest? Because, of course, it has friction acting against it. So we also know that while that block of wood is sliding on the surface of the counter or whatever it's on, we know that can't be conservation of momentum because we are losing energy to friction at that point. And so as soon as we have that, and that's an external force being at work, no conservation of momentum. Okay? However, there is still conservation of momentum here. So the bullet is projected out of the gun. And then as soon as it hits the block in the wood, I'd say in that first millisecond before friction has been able to act, of course, the bullet rapidly slows down, but the wood block rapidly speeds up. So just that millisecond before it really starts moving and friction has a moment to work, so that time where the bullet is coming to rest inside the wood block versus when it was first shot out of the gun and had its initial velocity, I'd say that is conservation of momentum, because from the point where the bullet leaves the gun to the point where the bullet stops inside the wood block would be no external forces acting other than when we're considering the system being the bullet and the wood block. Okay? So we have kind of a mixture of things happening here. Okay, so we want to know the muzzle speed of the bullet. So again, we need to kind of look at when can I use conservation of momentum, when can I not? So here we go. So that is the first moment at which the bullet is just going here. So I'm going to call this position 1. Again, I'm kind of looking at this and I'm going, okay, well, in this question, it looks like I'm going to have more than 2 kind of positions. So that's when I start numbering them 1, 2, 3. So here I have a block of wood sitting on a surface. Okay, so I'm going to call this position 2, and then we'll call position 3 the point where it comes to rest. Of course, that's when it has gone a distance of 9.5 meters on a surface that has a coefficient of friction of 0.25. Okay, so I want to know the velocity at this point. That's what I really want to know. I know the velocity at this point is 0, right? I know it comes to rest. And then I know the velocity of the bullet at position 2 is 0, but I don't know the velocity of the wood block at position 2, right? But now I'd say those are kind of like a combined thing, right? Once it's at position 2, you have the bullet and the block. So here, I don't know this velocity, okay? So I'm gonna need to find that if I ever wanna find the initial speed of the gun, because again, from here to here, position 1 to 2, I can use conservation of momentum, okay? That's where conservation of momentum is happening. I cannot use conservation of momentum from 2 to 3. I'd say the best thing to do here is, because we know there's a transfer of energy, is using the work energy theorem, okay? And so that's what I'm going to use in between here. Work energy theorem from here to here. Okay. So remember, work energy theorem is that the work is equal to change in energy, work being work done by the applied force and work done by the frictional force. And then and then of course we have our change in energies being our final minus initial. And we have a change in energy here, right? We have kinetic energy at position 2 changing into, well, really just friction. It's all being lost to friction at position 3. So really that's kind of what we got. So what I'm thinking, again, this is a really tough question and it's something that you really got to think, but basically I know if I want to use conservation of momentum in between 1 and 2, well, I need conservation momentum at position 1 or in all the momentums at position 2. And position 1, the wood block, right? I have a momentum of the bullet and the momentum of the wood. And then afterwards, I have the 2 of them together. In order to find the momentum of the bullet, before I need its velocity, oh, that's what I'm looking for in the end. Of course, the wood block before is going 0, so that's 0. The momentum of the block and the piece of wood together. Again, we're talking right at the point where the bullet stops and it just starts moving, but friction hasn't had the chance to act yet. I need that velocity there, because then I can use my conservation of momentum. So I'm going to use the work energy theorem to figure that out, because I know it has a bunch of kinetic energy at position 2, and that's all being transferred into work done by friction by position 3. So that's, I think, what we're going to do here. This is the work energy theorem. And then that, I can use that to figure out the velocity at 2 of the bullet and the wood block together, which then I can go back and use conservation of momentum to find the velocity of the bullet. Okay? So that's the best way I can see of solving this thing. Is this the only way? No, because at this point in physics, you have a lot of different ways to find stuff. But I'd say that's probably the best way, the easiest way. And there actually may not be another way. I'm genuinely don't know. I know that this is definitely the way that I would do this. Okay, so let's start with our work energy theorem, just really quickly, remembering that that is the work done by the applied force plus all my initial energies should equal all my final energies plus the work done by friction. Okay, and then keeping in mind we have no really applied force. Obviously the applied force was the bullet, but we're already assuming that there is kinetic energy initially, right? And why is there initial kinetic energy? Well, because of the force of the bullet. But the thing is, the force of the bullet isn't moving throughout this whole motion. It was just like worked really, really fast to get in, lodge itself into the block, and then we don't have that applied force being applied throughout the whole movement, okay? So really we just have the applied force, initial applied force just gave it initial kinetic energy, so that's in there. There's no final energies, right? Because at position 3, it's come to a rest. There's no gravitational potential. There's no spring potential, but there is work done by friction. So really, this whole thing becomes initial kinetic energy is equal to the work done by friction. Okay? So let's go over to this position or this page to start doing that. And so again, what do I have? I have my initial kinetic energy is all being transferred into friction, so it's equal to the work done by friction. So that's 1/2 mv squared, and remember that's v at position 2, is equal to work done by friction, which is force of friction, times displacement. Okay, we need to find force of friction, which is of course mu Fn. So if I go back here, I know that force of friction is equal to mu Fn. If I need Fn, well, I'll just draw a quick little free body diagram here. Well, look at that. I know Fn and Fg are directly opposing each other. If I look at my net force equaling mass times acceleration, well, in the y direction, it's not accelerating. So Fn minus Fg is equal to 0. So Fn is equal to, guess what? Fg, which is mg. Okay, so we know a few more things then. So 1/2 m velocity at 2 squared is equal to mu Fn, which is of course mg, times the displacement. And I think we have everything. So remember, this is the mass of the bullet and wood block together. We might need, so we have a 15-gram bullet and a 1.1 kilogram block. So I'm going to have to add those together. Keeping in mind, we have to change 15 grams to kilograms, which of course would be, 0.015 kilograms. Okay? So let's do that now, except for, I just realized, actually, do we care about mass? Because there's mass on both sides of this equation. It actually cancels out. So if you didn't cancel out the mass, it'd be fine. But actually, after I said all that, I realized, no, never mind. We don't need mass. So to solve for velocity at position 2, we have 2 times mu times g times d, and you just square root that. And look at that, we can get the velocity at position 2. A mu is 0.25. G, of course, never changes, unless you're not on Earth. And the displacement, again, was 9.5 meters. Square root that, and we get the 6.83 meters per second for the speed at position 2. Okay, so that's what I just found here. This is 6.83. Of course, I'm just writing it to 3 significant digits right now. I'm not worried about the actual significant digits needed. And when I plug that into my calculator for the next part, I am going to use the full value on my calculator, not just 6.83. Okay, now I can go over to conservation momentum from position 1 to position 2. So I'll actually just say the sum of momentums at position 1 is equal to the sum of momentums at position 2. Okay, and that's of course the mass of the bullet times the velocity of the bullet at position 1 plus the mass of the wood block times the velocity of the wood block at position 1 is equal to the mass of the bullet and the wood block times the velocity of the bullet and the wood block at position 2. Okay, we know that the wood block is initially not moving at all, and so that can be crossed out to be 0. And then we see here that if I want the velocity of the bullet at position 1, well, I just need to divide both sides by the mass of the bullet. So this is the case in which we actually need to make sure we know the mass of the bullet and the wood block together. Okay, so remember, mass of the bullet was 15 grams and the wood block was 1.10 kilograms. And so I got to add those together, making sure I turn 15 grams into kilograms. But when I do that, so the bullet at position 1 So we have 0.015 kilograms. Oh, didn't mean to do that. Plus 1.10 kilograms. That's going to be their combined mass times the velocity. And of course, we found their velocity at position 2 to be 6.83 meters per second. Again, I'm not actually going to type that into my calculator. I'm going to type my previous answer in. And then I'm going to divide that by the mass of the bullet, which is 0.015 kilograms. And I get the initial velocity of the bullet to be, well, at this point, remember, now we're going to look at our significant digits, which we used this one with 2. We used one with 3, but then it looks like all the other ones we used are with 2 significant digits. So this better be at 2, so that'll be 5.1 times 10 to the 2 meters per second. And that's that. We did it. Yeah, really difficult question. Don't worry if you can't come up with this plan right away. Obviously, that's just something that once you try a bunch of stuff, you eventually just get to it, right? And the more questions you do like this, where you're going to have to use a mixture of what you know from Physics 20 and 30, the better you will get at it, because you'll start recognizing when you can use conservation of momentum, when you can't, okay? That's all it is for conservation of momentum. So aren't you so excited after that question to add a second dimension into this? Because keep in mind, this is all with one dimension. And now we're going to add a second dimension into it. The good news is if we ever need to use energy in 2 dimensions, well, of course, energy and work are not vectors, they're scalars. So then we don't have to break those up into X and Y directions, but we do for momentum, and that's what we're going to do next.